Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Plane Stress and Plane Strain, and it is going to introduce the elastic constitutive models. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the plane stress and plane strain before wrapping up with conclusions. Analyzing solid mechanics problems in 3 dimensions can be really hard work, and it can get very complicated very fast. Fortunately, in a lot of cases, there are simplifications we can use to reduce a 3-dimensional problem to a 2-dimensional, one making it much easier to solve. The 2 main simplifications which are frequently used in solid mechanics are the plane stress and the plane strain conditions. In the introduction, we are going to take a look at a material property, Poisson's ratio. It gives us key information about how different materials deform under loading. Take a little orange cuboid. If we apply a compressive force to it, it will expand in the directions which are perpendicular to the direction in which we are applying the load. We call the direction along which the load is applied the longitudinal direction, and we call the perpendicular directions the lateral directions. If we reverse the direction of the force to apply a tensile load, the cuboid will obviously extend in the longitudinal direction, and it will contract in the lateral directions. The key concept here is that when you apply a load to a material in one direction, the material will also deform in the lateral directions. Poisson's ratio is the parameter that tells us how much the material will deform in the lateral directions. To define Poisson's ratio more precisely, let's take a closer look at the case where a tensile force is applied. When we apply our longitudinal load, it turns out that the resulting strengths in the lateral directions are equal, and they are proportional to the strain in the longitudinal direction. The ratio between the longitudinal strain and the lateral strain is actually a material constant. We denote this material constant with the nu, and we call it Poisson's ratio. If tensile strengths are assumed as positive and compressive strengths are negative, then the minus sign is just there, so that for the typical case where the lateral strengths are opposite in sign to the longitudinal strengths, we get a positive Poisson's ratio. The Poisson's ratio is also a key parameter in plane stress. Next, we are going to take a look at plane stress condition. When a point of a body is acted upon by stresses sigma x and sigma y in mutually perpendicular directions, the strengths are found by superposing the strengths due to sigma x and sigma y acting separately. The rectangular element of material in the left-hand side picture is subject to a tensile stress sigma x in the x direction. The tensile strain in the x direction is sigma x over E, where E is Young's modulus. The compressive strain in the y direction is negative nu times sigma x over E, where nu is Poisson's ratio. If the element is subject to a tensile stress sigma y in the y direction as in the middle picture, the compressive strain in the x direction is negative nu times sigma y over E. The tensile strain in the y direction is sigma y over E. These elastic strains are small, and the state of strain due to both stress sigma x and sigma y acting on simultaneously, as in the right-hand side figure, is found by superposing the strengths of the left-hand side picture and middle picture. Taking tensile strain as positive and compressive strain as negative, the strengths in the x and y directions are given as these equations. These are the elastic stress-strain relations for 2-dimensional system of normal stresses. When a shear stress tau xy is presented in addition to the normal stress sigma x and sigma y, the shear stress tau xy is assumed to have no effect on the normal strain epsilon x and epsilon y caused by sigma x and sigma y. when shear stresses are present, as well as normal stresses. There is therefore an additional stress-strain relation having the form in which G is the shearing modulus. Tau xy is equal to G times gamma xy, where gamma xy is the shear strain. Consider an element of material subject to a tensile stress sigma O in one direction, together with a compressive stress sigma O in a mutually perpendicular direction. The Mohr circle for this state of stress has the form shown in this slide. The circle of stress has a center at the origin and a radius of sigma O. The normal and shear stresses on an inclined plane are given by the coordinates on the circle. In particular, we know that there is no normal stress when 2 times theta equal to 90 degree. That is when theta equal to 45 degree. Moreover, when theta equal to 45 degree, the shear stress on this plane is of magnitude sigma O. We conclude then that a state of equal and opposite tension and compression is equivalent, from the stress standpoint, to a condition of simple shear in directions at 45 degree, the shear stresses having the same magnitudes as the normal stress sigma O. This system of stresses is called pure shear. If the material is elastic, the stress epsilon x and epsilon y caused by the normal stresses sigma O and the pure shear gamma xy under stresses sigma O. The strengths are expressed as these equations. If the size of the element are unit length, the work done in distorting the element is shown as the following equations. As the one state of stress is equivalent to the other, the values of work done per unit volume of the material are equal. Then we obtain E is equal to 2 times G times 1 plus nu in a bracket. The following relations between stress and strain applied for materials are expressed here. In matrix form, these equations can be written as this expression. This matrix form is called plane stress. This is a two-dimensional system of stress. Another two-dimensional system is known as a plane strain condition. If one dimension is very large to the others, the principal strain in the direction of the longest dimension is constrained and can be assumed as zeros, yielding a plane strain condition. This is a two-dimensional system of strain and a three-dimensional system of stress, as shown in this slide. We have two strains, epsilon x, epsilon y, and three stresses, sigma x, sigma y, sigma z. Then we obtain the three basic equations. After simplification and add shear equation, the strain-stress relationships are expressed here. We know the shear modulus G equal to 2 times 1 plus nu in a bracket over E. The following relationships between stress and strain applied for materials are expressed here. In matrix form, these equations can be written as this expression. This matrix form is called plane strain. From conclusions, what we learned? A material is said to be under plane stress if the stress vector is 0 cross particular plane. A related notion, plane strain is often applicable to very thick members. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.